Good morning. My name is Osvaldo Bascour, and I'm going to share at the COM 2023 at the 62 Annual Conference of Metallurgists in Toronto, Canada. The topic is called the maximization of water recovery and metal production in low-grade ore mines. In this case, the metal is copper and is based on a plant in Chile called Caserones. I'm very glad that we have been able to work with the people, Freddie, Simon, and many other people that contributed to this paper in one way or another one. My name is Osvaldo Bascour. I have worked 10 years at Penzuel, 25 years at OCSoft, which was PI. I wrote a book, and then wrote a chapter in the mineral processing and extractive metallurgy handbook on process control and operational intelligence. And now we are writing a book with Fernando Concha, one of my mentors. It's called The Science of Mineral Processing. Most of the work that is the fundamentals are going to be used in this presentation one way or another. The agenda that I have prepared for you today is based upon some common pains in the production processes in the mineral processing industry. We're going to look at some business processes which are really fundamental for these results to happen, and we'll talk about that. The digital twin is where we encapsulate a lot of the knowledge to maximize the metal production and water recovery by avoiding process constraint and equipment constraint. And we develop with the data that we collect the predictive model to support the dynamic decisions that needs to be done in real time. This is very, very important. This is not something that we take the data and we process it later. Now, this is in real time. We are providing an inference of the whole state of the plant, including the grinding comminution, the flotation, flocculation, and the thickening, and the tailing ponds. Everything has to be coordinated for these results that we are going to demonstrate here today happen. Other digital twin we have been put together early on in 2014 with ArcelorMittal in Quebec Cartier. We have some other work done in Anglo American, Barrick Gold, and this is Lumina Copper. And also we have done a lot of work in the power generation, in this case in DESA in some places. The key here is that when we are operating low grade ores, mines, and we are operating actually less than 0.5% copper, what we are processing is just rock. So we need to have that in mind. The amount of energy required to produce the same amount of copper is huge. And also the amount of water increases tremendously because the rheology becomes one of the constraints in the mill, in the cyclones, in the flotation, in the flocculation, and in the thickening. So that's what we need to monitor very carefully, so we have the right size particle distribution which enable to move the material with the less amount of energy, and of course trying to extract as much water possible in the thickening and in the tailing ponds. As you can see here, the copper increases exponentially as the copper grade decreases, and that's something very variable. So that's the major disturbance that we are sensing when we are trying to maximize the copper production in these low-grade ore mines. The water is going to be worse as we go. This is the prediction from the World Resource International Organization. In 2014, there are going to be many countries that are going to have severe problems. So if we want to extract more copper from Peru, from Chile, from South Africa, and some of the countries in Zambia or in Queensland and in India and Java and so on, and Mongolia, and again even in Spain and some other, we are going to have severe problems. So we need to look at how to float the material, and as you can see here, the major constraints are maximizing the net metal production rate, which is the ton, grades, and recovery, subject to water availability. So the water availability is what is constraining the maximization of the tonnage in these plants. So to maximize the net metal production rate, we need to find ways to maximize the water so we don't have problems with mill overload, idle cyclone open, low water recovery due to bad flocculation, and of course not good copper recovery. As you can see here, it drops down when you go in the lower end, fine particles or coarse particles. And this is the shape of the recovery curve where we see exactly what is the particle size distribution that we need. And that's what we need to control. We need to minimize the variability of everything that is related to this net metal production rate. So we need to first of all measure it. How do we do this? We model the whole plant in the grinding process, the flotation process, the water separation process, because this water that we are extracting here and we are adding to the system is coming from the plant. So we need to recreate this back. One of the major problems, as I said, the business processes needs to be reorganized. The data we have at all is all integrated in the PI system. The major problem is that people are not communicating the business process correctly and making the right decisions, the right training for operation coming from engineering, maintenance, and so on. So there is this big hole here that we need to pave, and we pave that with what we call a digital twin. So we encapsulate the whole knowledge, and if you can see the major business process that we are adding here that has been neglected in many plants is the integration of the plant with the water management. And this water management has to be done dynamically. So if we want to get the right recovery, we need to know exactly what's coming in, what is the weather, what's going on, what is the tonnage, and really maximize the tonnage by taking care that the water recovery is available. Otherwise, we cannot maximize the tonnage. It's useless. So the digital twin is basically using the online data that we have, the time series data, adding the right context. And this is the most important thing. So everybody can have access, and we developed and they developed the predictive analytics of grinding, flotation, net metal recovery, water separation, tailings separation, and by using the knowledge that we have and visualizing and connecting to their expert system, control system, so the loop has to be closed somehow. Basically, it's just managing the whole plant, the whole body. So if we have pain in the stomach, we know that that's coming because we ate, or the ore was not good, and we have indigestion, meaning that we ate too coarse, and we have problem with the time that we have, or the acid that we are generating here, or the digestion. It's the same thing that happened with the flotation, flocculation. If we don't have the right size distribution, we don't have the right flocculation for the retrieval of the water, the recovery in the thickeners, to have the right water so we don't choke when we are, in this case, grinding. So the grinding is affected tremendously by the right amount of water that we have available. And this is basically the spinal with all the sets of data, which is managed using an object-oriented environment, so we can model the rock processing. The water processing is the first factor, and then we optimize the mineral processing. As we go here, this is the way that the database looks like, and this is all done at the internal of the database. This is just the visualization, but the visualization becomes available for everybody to act. So we can act in the grinding circuit, and we can act using the models that have been developed over the years. This is DynaMill, DynaFloat, DynaThick, which we call DynaSoft Pro. And this is where we have a dynamic model, which is using the data to estimate the best possible size distribution as the outcome of the grinding mill by defining what are the things, in this case the waters, and what are the water additions that we need to maximize the copper production. The water production becomes our guidance on how we move, and we need to avoid violating costly constraints and reduce the variability of the grinding product to improve flotation, flocculation, thus the thickening and the water recovery is improved. And we do that by managing the size distribution, and you can look at them. We can see this fractal way on how we measure this. This cannot be anything. This is very critical what we have in the cyclone overflow. The cyclone overflow is critical. And there we go now into flotation. We have to generate the right bubble for the size distribution, then have the right froth so we can separate and eliminate the pyrite and all the gangue from the copper and moly. We are using the DynaFloat, which is a dynamic model in which we put that into a bank, and the bank has to find the right profiles as we are explaining in the paper with detail. Basically here I'm just going to do a screenshot. We are tracking the net metal production rate subject to water, and we are looking, and here you can see a 23 compared to 15 because we are really changing the way that they have been operated in the past, and we are able to improve tremendously, as you can see here, by doing the right grinding, doing the right hydrodynamics of the bank, and having the right hold depth, so we have the maximum amount of bubbles that is possible depending on the flotation system that they have. The models are all related to ore types, so we have cases, and each case you have different type of correlations, but most of the correlations are indicating that the particle size distribution, the water additions, and the rheology are the major variables. Here we see clearly that when we are running low, of course, everything is fine, but when we start pushing the mill into the 4,700 tons per hour, the copper recovery and the copper production drop drastically at 200 microns here and at 68% solid. But really the major problem of this problem is the fines created in the mine, as you are going to see later. So this is the recovery of the water in the three thickeners. There is a pre-classification, and there we are measuring the water coming out, which goes from 4,000 to 600, giving us enough water to create the right particle size distribution, which enable us to generate the amount of water necessary. Here we explain that if we maintain the right size distribution, we get into this red zone where we are generating more than 600 tons per hour. If we don't have this little number here, which is the particle size distribution shape, we get too many fines and we coagulate instead of flocculation. Basically here I'm just showing that not only we are losing water, we are also losing copper, because sometimes the flotation cells are not equipped properly with the right hydrodynamics. So we are trying to maximize the turbulence to generate the bubbles and have the maximum amount of hold up so we can catch as much mineral as possible. Then we clean it. This is showing that the particle size distribution is one of the most important variables in the water recovery model. This shows the whole plan, an integrated view of it, in which we have the right grinding, the right flotation, the right thickening. Basically, it's the flocculation by having the right size distribution, so we can have the right energy for the particles to coagulate, eliminate the water, and that's very clearly defined in some cement papers, where if you don't have the right shape, you entrain water down to the pond rather than being able to put it clean, and that's the water that we have here to create the right size distribution. So, in summary, to maximize the copper production, we need to first recover as much water possible, which is necessary to maintain the right ratio of water to tonnage, so we get the right production of copper and the right amount of water coming out of the plant. As I said, we have applied this into many others. I don't have enough time to go in detail, but if someone has time, I'd be glad to answer some questions. The details are that we put together this digital twin to transform the information available from the plant in real time, so the user can have the desired degree of detail. We use dynamic process model to increase the visibility, to improve the decision support, and to increase the copper production by 32%. And that's the potential that we have if we have the 40% water with the right flocculation that provides this improvement in the metal production. We use the OSB digital twin, which is based upon the BICE system, and then we improve the efficiency and sustainability to process low copper ore grade. That's it. Thank you, and I'll be glad to answer any questions.